Hello everyone, so in this video I want to look at how we can use the standard cell potential to determine whether or not a reaction or a redox reaction will be product favored at equilibrium. So I've got a couple of reactions here for us to look at and determine whether or not they will be product or reactant favored at equilibrium as written. So at the moment they are written as if they are product forming, so they are written as species plus species gives certain products, but it's just in principle to give us a starting point for the conversation. So what I want us to look at, so specifically for A, for example, so let's try and recognize first for the forward reaction, what are the species that are being oxidized and being reduced, right? So in the forward case, we can see that copper solid would need to go to copper 2 plus 2 electron, right? So it's being oxidized in the forward case, and iodine solid is being reduced, right? It needs to go to it needs to gain iodine solid, I2 solid will need to form 2I minus, right? And it will need to gain 2 electrons to undergo this process. We can actually write it as such. Right, so that is what happens in the forward case. So meaning if the forward reaction occurs, these are our species. So that means in the forward situation or the forward scenario, copper solid undergoes oxidation. So that makes it our reducing agent. Right? And because iodine solid is undergoing reduction, it makes it our oxidizing agent in the forward direction. Right? So that means forward, that is what we need to consider. If the reverse reaction, so meaning the reverse reaction, and this written as such, so reverse, which species is being oxidized and which species is being reduced, right? So in the reverse sense, copper 2 plus is aqueous, is gaining 2 electrons, and it is forming copper solid. Right, that is what's happening in the opposite sense. So in the opposite sense, this becomes copper is being reduced, and of course then it means that 2I minus aqueous is being oxidized, and it needs to proceed to form I2 solid plus 2 electrons. Alright, so in the reverse case, it means that copper 2 plus being reduced must act as the oxidizing agent, and I minus would be the reducing agent. So the question is, in which case, or which species is the stronger oxidizing and reducing agent? So let's compare reducing agents. So let's compare reducing agents. Right, so the reducing agent options that we have, in the forward direction, it would be copper solid, and in the reverse direction, it is I minus. All right. So meaning if copper solid is the stronger reducing agent, then the forward direction or the forward reaction is the favored reaction. If I minus is the stronger reducing agent, then the reverse reaction is the favored reaction. All right. In comparing oxidizing agents, the forward reaction is I2 solid. All right, remember this is aqueous. I forgot the aqueous here at the top. Aqueous. Right, iodine solid is our forward reaction champion, and the reverse reaction, copper 2 plus, is the oxidizing agent. All right, so now let's look at the standard cell potentials in each of these cases to see which one is the stronger candidate. All right, so actually let's first see what we are going to compare. So let's look at the reducing agents first. So we need to look for copper solid and iodine minus. All right, so where is copper solid and iodine minus? Okay, so here's iodine minus. Right, here's iodine minus and I2. There is its reducing half reaction. And copper solid, there it is. There it is. All right, so copper solid is below iodine minus. Right, it's below iodine minus. So there's iodine minus. And there is copper solid. Right. So that means that copper solid is a stronger reducing agent than I minus. Okay. So copper solid is the stronger reducing agent. Why? Because one, it lies lower, it lies below I minus on the standard reduction potential table, and also it has a lower standard reduction potential, right? And it means actually that copper solid wants to be oxidized. That's actually what it means. Copper solid wants to be oxidized. I minus does not want to be oxidized. That's actually what it means inherently by it lying lower. So it means copper solid wants to be oxidized. I minus wants to be reduced rather. So that's making it a better reducing agent, right? So a reducing agent, remember, is something that wants to be oxidized. So copper solid preferentially wants to be oxidized more so than what I minus wants to be oxidized. Okay, right, so that's what we actually were comparing. So it wants to be more, it wants to be oxidized rather than I minus. And that's what we just saw on the table. Our next question is to compare the oxidizing reagents. In other words, these are things that wants to be reduced. So the question is, does I minus want to be reduced or copper 2 plus want to be reduced? And hopefully your intuition should tell you that I2 would like to be reduced preferentially over copper 2 plus. But let's see what the table says. So we're again here, and we're still here that we see I2 lies above copper 2 plus. And we know that the strength of our oxidizing agents increase the higher they lie on the table. The reason is that this is we put the table in terms of reduction half reactions, right? So meaning the strongest oxidizing reagents are at the top of the table, meaning the species that want to undergo reduction, right? So the species that want to undergo reduction, in other words, the strongest oxidizing reagents, will be at the top. All right, so the higher a species is at the top here means the stronger oxidizing agent they are, the more they want to undergo reduction. So I2 is a stronger oxidizing agent than copper 2+. All right. So I2 solid is a stronger oxidizing agent. Okay. So now the question is, so we know copper solid and I2 solid are the stronger reducing and oxidizing agents. The question is, which side are they? They are on the left-hand side of this equilibrium. So in other words, if we mix copper solid and iodine solid, they are the stronger reactants, so they will drive a product forming equilibrium or a product favored equilibrium. So, and that's what we try to figure out, right? So we mix strong with strong to form weak plus weak, right? The same idea as with the acids and the bases. I mean, that's a horrendous parallel to draw, but it's the same kind of concept, right? It's a strong reducing agent plus a strong oxidizing agent, giving you the weaker the weaker oxidizing agent and the weaker reducing agent, and hence this equilibrium will lie towards the right, towards these products. All right, so this means this mixture will have a product favoring equilibrium. The alternative way that you can look at it is you can of course calculate something like E cell, but I mean we don't know really what is at the anode and what is at the cathode, so we need to do it as such. Alright, so let's look at B. So now you've got the gist of it. So you first look at what is in the forward reaction, what are being oxidized, what's being reduced, and then in the reverse reaction you look at what's being reduced and oxidized and you identify them. I'm just going to look at exactly what we need to compare. So in this case, hopefully you can see that again what is being oxidized and what is being reduced. Alright, so our pairs that we have to compare in this case is iodine solid and Cl2. This is a gas, yes, it's a gas. And Cl minus, aqueous, and iodine minus, aqueous, right? So just quickly to check ourselves, right? So iodine minus goes to iodine, or iodine solid goes to iodine minus. So to undergo that, it must undergo reduction. So it undergoes reduction in the forward process. It needs to undergo oxidation in the reverse process, right? So if it's undergoing reduction, the chlorine must undergo the oxidation in the forward process, right? So that's why we compare these species as that. So iodine undergoing reduction and chlorine gas, these are going to be our oxidizing agents that we compare. and Cl minus and I minus are our reducing agents that we need to compare. All right, so the question is, which is the stronger oxidizing agent between I2 and Cl2? So let's just get the equilibrium or the reactions that we need to look at. So we got I2, it's the same one that we looked at just before, I2. Now we need to find the Cl2, and that is of course there. So if we're looking at Cl2 versus I2, then we notice that, well, Cl2 lies above I2, so that makes it the stronger oxidizing agent. All right, so therefore Cl2 gas is the stronger oxidizing agent. All right, and comparing the reducing agents, Cl minus and I minus. All right, so I minus, here's I minus, and Cl minus is over there. We see that I minus is the stronger reducing agent because it lies below Cl minus. All right, so it's a stronger reducing agent. So in other words, it wants to undergo oxidation. So let's call it reducing agent. All right, so now the question is, on which side is Cl2 and I minus? And we notice, well, it is on this side, right? It's on the so-called product side as written here. So that means that technically on this, in this equilibrium as it's written, it is the reactant side or the product side that is the stronger side. So in other words, this will actually form a reactant favored equilibrium, right? Because the weaker side of reducing and oxidizing agents is our reactant side. So in other words, there is no way that there can be a product favored equilibrium. So it is a reactant favored, reactant favoring equilibrium. All right, so that was B. Moving on to C. C has potassium and Cl minus, giving us potassium solid and Cl2. All right, so in this case, in the forward reaction, we can see potassium is being reduced and Cl minus is being oxidized. All right, and of course in the reverse case, potassium is being oxidized and Cl minus, Cl2 gas is being reduced. So let's go ahead and make our pairs here. So in the first case, our oxidizing agents, so potassium plus aqueous and chlorine gas are our oxidizing agents. Right, these are the species that are being reduced, or that we identified as the species that undergo reduction. Right, so we said potassium plus was being reduced to potassium, or that Cl2 was being reduced to Cl minus. All right, and then in a similar fashion, Cl minus was being oxidized to Cl2, or that potassium was being oxidized to K plus. So Those are our reducing agents that we must consider or compare. So potassium solid and Cl minus aqueous are the reducing agents. Alright, so let's compare our oxidizing agents. So potassium plus and Cl minus. And if you look at where potassium lies in this table, well, potassium is way here at the bottom. So there's K plus, and Cl minus, Cl2, sorry, is what we're comparing. So Cl2 is much higher than potassium plus, and that makes a lot of sense, right? Because Cl2 would much rather want to be reduced than what potassium plus wants to be reduced. So it is clear that Cl2 is the stronger oxidizing agent. Oxidizing agent, right? So because potassium plus would not want to undergo reduction, it does not want to accept those electrons. Cl2 on the other hand really likes to undergo reduction. It wants to form Cl minus. Cl minus is a common ion that you associate with it. So let's see on the other hand which of potassium plus and Cl minus wants to undergo oxidation, in other words, which is a stronger reducing agent. So if we look at potassium plus, here it is at the bottom, and Cl minus is here at the top. And indeed, yes, potassium plus is the stronger reducing agent because of that fact, because potassium would rather want to be oxidized than what Cl minus would want to be oxidized. Right. So that means potassium solid is the stronger reducing agent. All right, so which side is potassium plus and Cl2? And indeed, it is again on our product side. So that means the reverse reaction is the stronger reaction in this case. And again, we have a situation where we have a reactant favored. Equilibrium. All right. So let's look at our last example. Our last example, it's a bit more difficult to see necessarily exactly what is going on, but let's look at the forward reaction first. So we see potassium is being oxidized to K plus, and then water is being reduced to hydrogen and OH minus. So that's the easiest way to do it. So potassium is being oxidized, so hence the other species needs to be reduced, and then hydrogen gas and hydroxide is being oxidized in reverse reaction to water, and potassium must be reduced to potassium solid in the reverse reaction. So that means the pairs that we are considering here in question D, of course, potassium plus aqueous and water, liquid, and that is for oxidizing agents. Right, so that's species that we identified as possibly being reduced. And for species being oxidized, so that was the potassium solid and the H2 gas and the OH minus aqueous. Alright, and that was for possible reducing agent. Alright, so let's first look at the oxidizing agents. So again, we're looking at potassium. So potassium is here way at the bottom. So potassium plus, in terms of oxidizing agent, in terms of being reduced, potassium plus rarely wants to undergo that. So almost anything above that, I mean, yeah, we just need to find the reaction to confirm indeed where it is. So where is water? Water. Here it is. So 2 water plus 2 electron giving hydrogen gas and hydroxide. So indeed, water in this case is the stronger oxidizing agent. It lies only a little bit above the potassium plus. So in other words, it would be preferentially reduced to the potassium because it is a stronger oxidizing agent. All right, so water liquid. Oxidizing agent, right? Because it would rather be reduced than what potassium plus would be run to be reduced. All right, and then the same for potassium solid and the others. If we look at that, potassium solid lies below the hydrogen and the hydroxide, so that means it would rather be one to be oxidized, that making it the stronger reducing agent, right? Because it lies below. So anything below, lower than what? So this is below the potassium solid is below this, making it the stronger reducing agent, right? Because it wants to be oxidized. So therefore, in this case, comparing those things, potassium solid is the stronger reducing agent, right? Wants to be oxidized. So if we look at where those species are, we see, well, we said potassium solid and water liquid. Potassium solid is the stronger reducing agent. Water liquid is the stronger oxidizing agent. So in this case, it would form a product favored equilibrium as written. Right, so therefore it's a product equilibrium. All right. Good. So that's comparing oxidizing and reducing agents when you have them reacting. And of course, that would give you also an idea how to set up a product favored equilibrium in terms of a cell. Also knowing which species needs to go at your anode, which species needs to go at your cathode, because you know which species wants to be preferentially oxidized, which species wants to be preferentially reduced. This builds towards that. All right, good. Thank you for watching, and I'll see you in the next video.